Good afternoon, everyone. This is Chris Posey, the marketing manager at OGI. Thanks for joining our webinar today, Pneumatic Heater Instrumentation Controls, P&ID, and available heater options. So our presenters today are Peter Udovinko, our Terry Sales Manager, and Grant Oden, who is our Engineering Manager. So as I mentioned in the chat console, this webinar follows on the last webinar that we did on July 16th called Water Bath Basics. It's not necessary that you had to see that one to understand this one, but they do kind of, they work together. So if you are interested in viewing that July 16th webinar, Water Bath Heater Basics, I've posted the link to that in the chat console. So speaking of the chat console, we'll be doing a Q&A session after the presentation. So as we're going through, if something pops into your mind and you have a question about it, then type it up over there, and we'll take a few minutes at the end to address all the questions that come in. So one final thing I would mention, if you or a colleague or a friend is having problems connecting, they might consider changing networks, or we've heard from a couple of people that there could be a network or firewall issue. So if you're in contact with someone who's trying to get in and can't get in, you might encourage them to utilize an alternate network. So that's it for me, and with that, I'm going to go ahead and turn it over to our engineering manager, Grant Oden.
Thanks a lot, Chris. My name is Grant Oden, engineering manager. I'm just going to give you guys kind of a basics, a primer on some heater instrumentation and controls. So the outline I'm going to go through is the heater P&ID. What is it? What are the features of it? How do you read it? And then the next part of my presentation is going to be on the controls. We're going to look at how controls are really affected by different variables in the system. And then, of course, Peter's going to have his section on heater options. So when talking about heater P&IDs, or P&IDs in general, a lot of people have heard the term P&ID come up. What that actually stands for is piping and instrumentation diagram. This is a graphical representation just using symbols. So think of it like a roadmap. It's not intended to necessarily show you physical orientation, but it's going to show you where in the process different key components are. Okay, so we're going to see an example of that where you might see a piping run appear to be kind of going in an upward or downward direction on a P&ID, but physically it could go the other direction. It's not incorrect, it's just showing you kind of the flow and how things are connected together. The right side of my screen is some typical symbols that you're going to see. These are going to show up on the example P&ID I'm going to show you. A lot of these are industry standard. We've got a few that we've kind of modified, but these follow basic ISO standards, so you'll see some of these symbols come up in other ways. So it's kind of a legend for you. So if you want to come back and look at this presentation later, you can kind of refer to this. So I'm going to be going over a very basic P&ID. This is a P&ID that we've used here at OGI many times. It's what we would consider a standard, if you will. This particular setup is pneumatically controlled as opposed to electric. By far the most common type of system and controls we use. Many other different types of ways to control a heater, features, functions, all kinds of stuff, but we're just going to kind of focus in on something basic, and this is going to represent a whole lot of heaters in the field. So I've broken this P&ID up into little sections, okay, so A, B, C, D, and so forth. We're just going to take it a step at a time as we go through, and we're going to follow that process path through the process coil, up through the fuel train, and we're just going to follow section by section, and I'm going to show you each of the system components as they physically are shown on a heater. So starting out in the section A that we referred to on the P&ID, this is the fuel train where it's going to tap off of the coil outlet. In 99% of the cases, you're going to want to bring your fuel train off of the outlet. The main reason for that is you want to ensure that it's warm gas that's going to your burner. So we're going to put we're going to run it through that coil, heat it up, and then the first thing we're to come to as we tap off is our BV100 ball valve that isolates it at the most extreme end of the piping string. So we're going to follow this along, and the gas train comes to the next major components. That's the strainer, the STR100. The strainer is it's kind of a filter. There's not a micron rating to it per se. It's just kind of getting any larger contaminants or particles that can come into play and could damage any components. There is a ball valve BV100A mounted on this strainer, so you can isolate and drain, and then remove the screen. The screens are typically cleanable or replaceable, whichever. Kind of depends on how much contamination there is. So after the strainer, we're going to go into the preheat coil. So you'll see this pipe go into the side of the shell, and we're essentially going to heat this gas twice to be doubly sure in all conditions we've got warm gas going to our burner. We don't in any way want any liquids or precipitates coming out because of it being too cold. So we're just going to run it through again. It's basically just a pipe that goes into the side of the shell, is immersed in the bath, and comes back out. All right, so here we're going to show you the first cut and metering section, is section B on your P&ID. So you can see we come out of the shell, come straight out. So we've got, again, double warm gas coming through. The first thing we come to is PCV100. That is the first cut control valve. Typically, systems will have a 60 PSI cut at this point. Immediately downstream of that, we have a pressure relief valve, PRV100. Anytime we have a pressure cut or a different section in the system, we're going to put a relief valve to protect any components downstream. You're going to see that as a common theme as we go through. So after the relief valve, we're going into our meter run. This is the meter block and bypass loop. So as we're flowing from right to left, the gas has two paths to go. It can either go kind of this vertical direction through the meter, MTR 100, and then down the other loop, or go through straight across, where it really just bypasses that. And this is one of those examples where you see the P&ID not matching the physical way the equipment is set up. So you may recall in the P&ID, there was a kind of a loop that went kind of downward, the southward direction. This one happens to go up. Again, it's not an error. It's just kind of, showing you a graphical representation. In this particular case, you can see these ball valves, kind of an easy way to kind of tell where ball valves are, open or closed, is 99% of the time, ball valves with their handle at a 90-degree angle to the body are closed, and if it's in line with the body, it's going to be open. So unless somebody has taken the handle off and rotated it for some reason, this is a good rule of thumb, just kind of to give you an idea when you're looking at it, is this thing open or closed? So based on this loop, we can tell that the gas would actually flow past this loop here. So we have an open valve here, a closed valve, and a closed valve. Okay. All right, so here's the pilot and control loop supply. The point of this portion is to really filter and regulate the instrumentation gas that's going to come through and really do our controls. I'm going to go into this in a little more detail when I get to the actual control philosophy section, so you can see how this really works. In this case, we have a pressure gauge, so we have an upstream pressure indicator. We have a ball valve, and for those who have been paying attention, this one is closed because of the handle. We've got a filter, FLT 200. This is an actual kind of a micron rated filter, if you will. It's replaceable and cleanable. We have a higher level of filtration here just because the instruments downstream are going to be more sensitive. Next, we have a PCV 200, pressure control valve 200. It's a coalescing regulator. This is going to bring the pressure down to something that the instruments can use. And as I said before, anytime you have a difference in pressures, a section of the system that's got a higher or lower pressure, you want to make sure that you have an individual relief valve protecting that system. In this case, we've got a PRV 200. It's a little relief valve mat out here on the end so that it just allows for protecting those downstream components. We've got a pressure gauge, PI 200, and needle valve 200A. So you can see that we have a pressure gauge upstream and downstream of that regulator so we can see what the set point is. And of course, those needle valves are really just there for isolation purposes. So I don't know, if a gauge broke or if there's a reason to calibrate it, you could isolate that gauge, remove it, and then replace it. Okay, next we have the temperature shutdown control loop. So here's where we get to our second cut regulator, PCV 101. This brings the pressure down to something that the burner can actually manage. So we typically have a 5 psi pressure at the burner. This is further upstream, so the pressure at this point may be something like, say, 7 psi or something to account for pressure drop. And like we said before, common theme, we have a new a pressure zone, if you will. So we're going to need a relief valve. That's PRV 101. And here we have our shutdown valve, SSDV 101. So this, as the name implies, is a shutdown valve. We'll get into that kind of the control section. This is the one that's going to shut off gas if there's an upset situation, low water bath, high temp, and so forth. So we'll get into that in the second part. We also have the HTSD 108. That tag number is for the water bath controller. This is a pneumatic controller. It's got an adjustable set point, and it's going to limit the max bath temperature to 190F. We'll use 190F as a bath temp high for ethylene glycol mixtures 50-50. The main reason behind that is really oxidation becomes rapidly accelerated above that point, and we certainly want to be nowhere near the boiling point of any water mixture in the bath. On the left, you can kind of see a zoomed out and a zoomed out view, zoomed in, zoomed out view of the level switch. So we have a level switch at the 12 o'clock position on the end of our heater. And you can kind of see a zoomed in view of it here. This is we call it a switch, but it's not an electrical type of switch. This is a pneumatic switch. Electrical ones are available for electrically controlled systems, but again, this is a pneumatic example. Level switches, we normally mount them at the 12 o'clock position in the shell and at a point where it's going to trip before any of your coils inside could possibly be exposed to air, be uncovered by that water bath. That would be really bad. You'd start scorching and coking. You could, well, it'd lower the efficiency of the heater because you're not exposing the gas to a surface area. The other place to put a level switch is up in the expansion tank. You can kind of see that a little bit on the upper right-hand corner. It's just another way to do it, another location. But again, as long as you're not exposing the coils and uncovering them, then everything's just fine. So next we're going to get to the heater control loop part of it, the temperature control loop. So if you can see on that right-hand picture, this is a shutdown valve on the right that we just looked at. And then the next thing we've got is the TCV 101, temperature control valve. This is the valve that's really doing most of the daily work when the heater needs to get a call for heat, when it needs to cycle on and off. This is the one that's doing that. And we've mounted a speed control SCV200 to it. The reason for that is you really want this valve to snap shut, but then open at a very smooth, controlled rate, so you don't have a situation where you blow out the pilot or you cause backfires or anything else, okay? And kind of the left-hand part of this, you can see a closer view of that TCV and the speed control. So there's kind of an adjustment on top of there. So you can slow that firing the light off so that you get a good flame right off the bat. We're depicting the total arc relighter, as you can see in this picture. This is our in-house design. SVP 101. So it's a solenoid control that's mounted on the side of this. And again, we'll look at what that solenoid does and how a relighter works just briefly in the next part of the presentation. All right. So here's a pilot assembly. We're kind of at the business end of the heater. There's a lot going on here, a lot of little smaller parts, little things, but this is the part where we feed that pilot with gas. We have a FSG200 flame safeguard. This has a sensor. You can kind of see this coiled up copper line that goes in. The sensor is in the flame of the pilot. It's monitoring that the flame is present, and it's going to hold this valve open. As long as it sees that flame, it's going to hold this valve open. And if for something were to happen, pilot gets blown out, could be whatever the reason may be, it's going to initiate a shutdown. So just a purely mechanical and pneumatic device. We have a pressure control valve 301 going to our pilot. This brings the pressure down to its 5 psi that it requires. And then we've got a pressure indicator 301 and a needle valve that you can monitor to make sure you're actually accurately getting that 5 psi there. It's kind of hard to tell in some of these pictures kind of where things are. So in the upper right-hand corner, we've kind of zoomed out a little bit on this heater. So you kind of see where in the world are we on this thing as we walk through it. So in the upper left-hand corner, we have NV301B, the needle valves. This is a better picture. You can kind of see our pilot in a drawer, if you will, assembly kind of pulled out from the heater so you can see what's going on a little bit better, and you can see where that sensor goes into the end for monitoring the flame. Okay. All right, so again, at the business end, we're at the burner assembly. This is where this kind of the last step in our fuel train before it goes into the burner. This is the external part of it. We have a pressure indicator 101. So this is really as close as we can practically get to that burner to read that pressure, see what's actually at the burner. Again, that's 5 psi is what we're shooting for. And of course, the needle valve NV101 to isolate it. And we've got a ball valve, BV101, at the very tail end. So if you recall, there's also a ball valve right at the very beginning. So we've bookended our fuel train at the very beginning and very end with the ball valve. And again, this one is in the closed position, presumably for shipping purposes. Okay. We're on the home stretch of our P&ID. This is the heater shutdown switch. This is a feature that is optional. It's not absolutely essential. I'll explain a little bit of how this works, why we have it, why you would want to have it in the control section. This one we just conveniently mount in a location on the support saddle so you can get to it. And it's used for customer alarms so they can see remotely, hey, what's going on? Something happened. There's some kind of trip you could find that out remotely. Okay, that's the end of the P&ID primer. So now everybody's an expert. We can go on to pneumatic heater control. So I'm going to show you a few key scenarios that happen in this type of situation, a normal and kind of an upset situation, and we'll see where pressure goes in the system and how that affects each of these components. It'll make a lot more sense when you can kind of see this at play. All right, this is the same P&ID that we were looking at the very beginning. This is the same P&ID that we just walked through. So we're using the same example. What we have here is a normal operation. So there's nothing wrong, there's no faults, no system issues, and the burner is on. So I've got two colors. The green color is the fuel to the main burner, and the yellow is the control pressure. So in this scenario, you can see that fuel in the green section is coming off the coil. It's going through all the basic components. You can see it's going through the meter instead of the bypass, all the way to the burner itself. So it's getting fed. You can also see the control pressure coming off. The control pressure is making its loop through the circuit. We are feeding the pilot system, and we're also holding open our temperature control valve and shutdown valves. When these valves see pressure at their sensing point, they're going to open. When they don't see pressure, they're going to close. It's known as a fail closed valve. So let's walk through the next scenario. You've got heater's been running, it's met demand, and now you've got the heater turns off. This is a normal situation. So here's your normal operation, burner off. The process temperature has reached a set point of 50 degrees. So you can see up here at the very top of the screen, we've got a temperature, a process controller. It's hard to see in the fine text, but it's 50 psi set point in this particular case. This instrument can be mounted on the coil, on the skid, but many times you want to mount that in your process stream down after your cuts. So in this case, the process temperature has reached its set point of 50 degrees, and this controller says, okay, I'm switching. I meet my set point. Now I'm going to turn off gas downstream. So you can see now there's no control pressure going to this temperature control valve. So the speed control is going to allow free flow in the closing direction. So it's going to snap shut. When it comes back on, it's going to restrict flow and then allow kind of a slow on, just like we talked about. So if everything's going well, you'll cycle between the previous slide and this slide, on, off, heaters meeting demand, call for heat, and the cycle continues. So let's talk about, what are a few things that can cause a shutdown situation? Well, one of those is that in this case, we've got a bath temperature that reaches 190 F. Again, that bath temperature is pretty important. We don't want to coke our fluid. We don't want to oxidize it. We certainly want to be nowhere near boiling anything in this. This is not a boiler. It's not meant to be. So that 190 degrees, this is a controller. Again, that's the one that's stuck in the side of the shell. So in this case, that controller has closed off. So saying, uh-oh, there's a problem here. It shuts off everything downstream of it. So no control pressure is able to get past it. It's basically telling everything else in the system, stop, something's wrong, nothing can start again. So as you can see, nothing downstream of it is getting any pressure. So our shutdown valve in this case is tripped. Also, our temperature control valve is tripped. So you kind of have a double block between these two valves. Our burner also, or the pilot rather, also turned off in this case. So that the high bath shutdown is really important that we just kind of really shut everything down. This is also a reason why you would want to have a pressure switch. So you can see that upper right-hand corner. It's kind of hard to see, but there's that PSL 108 that we saw that was mounted to that saddle. It's set at 4 PSI. So it'll trip. It'll give a signal. In this case, it lost pressure. So if unless it's under normal conditions, it's going to sense a fault and give a dry contact, either open or close, to remote operators. Say, hey, something just happened. The heater shut down for some reason, and then it can be investigated from there. Okay, the next thing we have is we have a low-level trip. So we have the level switch mounted in the side of the shell monitoring the bath. Say, for example, you have a leak, or through normal evaporation over long periods of time, the bath has dropped to a point where the level switch trips. So it has a vote, if you will, just like the other shutdown components. And this one's saying, hey, my condition's not met. I don't see that level there. I'm going to shut off. So it shuts off, and it doesn't allow any pressure downstream of it. So nothing downstream is the same situation as the bath controller. The shutdown valve closes, temperature control valve shut. They both snap shut. Pilot's off. Pressure switch is tripped. Okay, now let's look at how our total arc would react in this situation. Our total arc stays on in case of a power loss, if you have batteries, or if there's some kind of failure in the circuitry. So it will not kill your burner. You're still going to be able to function. However, if while it's operating, it's sensing the pilot all the time. If it senses the pilot loss, so it has a sensor on the end of the pilot. If it senses that there's no flame there, it'll shut off the burner. And the way it does that is through the solenoid, that SVP 101. If you recall, that's the one that's mounted in the side of the total arc relighter. So we turn off that valve, and now look, we've turned off the gas to the temperature control valve, and therefore stopping gas from getting to the main burner. Okay, so that's the walkthrough of the heater controls and P&ID. That's the basics. Heaters can get more complex from here. They can get into more complex controls, more electronics, more safeties, more backups. But again, this is kind of the basic idea, basic standard of a system that we would ship. And with that, I'll hand it over to Peter, who will talk about some available options.
I wanted to mention before I do kick off my portion is that I know certain customers do not want any relief valves, which we can comply with, and they want more of a worker monitor setup. So again, it's not limited. We talked about having reliefs on everything, but that's, like Grant said, that's a very standard. If you don't have a preference, this is probably what we'll offer. However, I know more and more customers are becoming cognizant of any kind of leaks and the emissions and things like that, and so they don't want any relief valves, and we can do that as well.
Yeah, good point, Peter. Thank you.
So let's talk about available options. Essentially, this is things you can add to your heater, and this is not an exhaustive list by any means. It's just some most common things that we've seen. And the first thing I want to talk about is the relighter options. The Total Arc is our own in-house designed and built device, which we put out. I think we started in 2013 after 2 years of R&D and doing in the field testing, which the serial number 001 still working flawlessly up in the Upper Peninsula of Michigan. But that is something that we designed because we've had issues with other relighter type systems, and relighter systems that used to be available are no longer available that had issues. But you could besides Total Arc, customers also use Spitfires. You have Profire out in the marketplace, which has different variations to their models. Honeywell burner management systems also available. This is more high end. You could do more electronic controls with it. And we usually go with this setup for compressor stations or, for fuel gas heaters where we may be putting on a Allen Bradley PLC and communicating with the gas turbine. So this is more for a high-end application. On a general meter and regulator station water bath heater, you probably wouldn't want to put that on. But I do know some customers have very stringent safety standards that they're trying to develop and advance, and they want all kinds of redundancies, and so they may want to use that. And then obviously the very simple end of that would be a push button where you would have to come out and relight it, even if a gust of wind, say, blew out your pilot. The nice thing about a relighter is it will relight it, and if it senses any loss of flame on the pilot, then it'll automatically try to relight it. And if it can't, then you have an emergency shutdown. Different relighters will have different number of attempts, and that just kind of goes into what your preference is. So that's just a relighter portion. Some people don't use any relighters. We have customers that use a manual relight where they will have to use a kind of like a stick, a flame on a rod or rag or something like that. For those cases, we say at least use a push button. And I know some customers have a policy that if there is any kind of a shutdown, they need to send a technician to do an investigation and see what's wrong before they can relight it. And so we understand that. But if it could become a nuisance where a gust of wind blows out your pilot and a relighter can immediately relight it without, provided all your other safeties are met, like your level isn't too low, your bath isn't too high, things like that. So that kind of completes the section on the relighters. Next, I want to talk about is skid mounting, and essentially on larger units, it's nice to purchase the heater with a skid. Helps with loading and unloading, kind of keeps it all together in a modular fashion. And then we also can do, and when I say us, I think this is from water bath heaters in general. These are options available through most, I would believe. You could do also containment skid, where maybe your unit is near a protected wetland or marshes, and so we build these to hold 110% of the water bath volume. And I know there's a difference. In the first presentation, we talked about the differences between propylene and ethylene glycol, and the biggest takeaway from there is that propylene is a lot more environmentally friendly, so I know customers use that. We actually have some customers that will use propylene glycol and use the containment skid as a kind of a protection to make sure that there's no leaks, and if there is, it could be all contained. And available options include recommended spare parts. This would depend on the type of a relighter and the controls that you would have. For us, we would actually include these at a discounted rate when you buy the equipment. So again, just kind of a good to have these on hand, especially when it's startup or commissioning. For some reason, something did fail, you'll have another part to quickly install and continue with commissioning. And then the other option I want to talk about is the fuel gas meter. Pictured here is a Roots meter. This is kind of our standard. However, if you have a preference for something else, we could use that as well. I'm sure any other manufacturer have the same kind of, just let us know what you want and we'll be able to include that. And then if you do buy your own meters but you want to be able to install on your own, then you could also get this option. It's what we call a 3-valve bypass. Essentially, we provide the piping and the block valves and the spool piece. Just tell us what those dimensions need to be, and we can size it properly. When this arrives in the field, your technicians would remove this spool piece and install your own meter that you prefer. And then stack insulation. Biggest advantage to this is personnel protection. We discussed the low water level switch, and it's generally located at the top. As you can see in this image, you've got 3 stacks, very limited space to reach around and access it. I know a lot of customers want to test that every year just to ensure that it's functioning properly. So having that insulation there is very inexpensive way to protect personnel. But the other part of the another benefit of this stack insulation is to kind of keep that exhaust warm air warmer, so that it promotes better drafting. And then if you do purchase one of our low noise flame arresters, we would recommend you buy this as well. It kind of helps with noise dampening as well. Next option would be draft controls. This is an augmented flame arrestor, and essentially what it does, first of all, it's for areas where you may have high wind situations, and it'll prevent from your pilot blowing out. And the way it works is when your burner turns on, there's a draft diverter plate that opens up to allow the air to flow in to the flame arrestor, and then when the burner turns off, it closes back. And the benefit of that would be, here's the diagram, kind of what that looks like, and the actuator uses that instrumentation air, that 20-pound pressure, to open the plate on the left-hand side and kind of open and close as the burner comes on and off. So again, when your burner isn't working, the other benefit is it prevents air from moving through the flame arrestor, the fire tube, and out the exhaust, which could then also pull out the heat. So by closing that off, you're kind of keeping it more efficient, and you're preventing from heat unnecessarily to escape, but also prevent from a gust of wind blowing out the pilot. Where you see the word flame, that's a flame cell element. That's this spiral wound cylindrical shaped flame element, and its purpose is to allow air to be drawn in for combustion support, but prevent flame from propagating outside of this flame arrestor, outside of your to your station. And essentially the flame arrestor is what separates your general wiring inside of the flame arrestor and class 1 div 2 area outside of the flame arrestor. Next option is an enclosed gas train. As you can see, there's a cabinet with insulation, and this was designed for certain customers in very cold climates, and maybe a situation where they want to keep the gas train outside of the elements, kind of keep it protected. For this cabinet, we cut away the insulation to be able to use that radiant heat from the shell and keep that area warm, and kind of closes in with insulation, keeps it nice and warm. Next option is what we call an elevated air intake. As you can see, it's got a snorkel on top of this flame arrestor. Typically, air is drawn in horizontally through, on this side it would be on the left-hand side down where the flame arrestor is. But in this case, you've got air coming in from the top. And the reason for that is, next slide has a image of a station that gets a lot of snowdrift and kind of buried the heater completely and prevented the air from coming in and basically clogged it up. So this is specifically for those conditions. We also offer staircases. Some of our customers want to ensure, for safety reasons, that if their technicians are carrying anything up to the top of the heater, whether they're topping off the adding glycol or doing any kind of work, that they use a staircase instead of a ladder and platform. So that's another option available. And we do have a service department that can do anything from startup services to preventative maintenance. We can also do retrofits and upgrades. If you have an older heater and you want to put on a relighter system, say you've got a push button, or maybe you don't have a relighter system at all, modernize it, bring it up to code, we would be happy to do that. And I know some customers actually want to add it on a new heater to the capital expense as opposed to an operational expense. So, it kind of depends on how you want to do it. But the point is, we do have a service department who can dedicate to doing complete service after the sale. And that completes the section on available options. If you guys have any questions, please type them in. If you think of anything, Grant, if you move to the next slide, we'll have our information here. Send us an email, give us a call. We'd be happy to answer any questions. And of course, if those of you that we work with, if you do want us to kind of walk through your design, I know everybody has a different, unique way of wanting to do controls, or maybe you're wanting to develop something, let us know. We'd be happy to work with you and our engineering team to kind of come up with something. So this is just a standard, an example of one. You don't have to design one that way, but that is a basic setup that we've used for many, many years, and we've had a lot of success with.
All right. Well, thanks a lot, guys. That was some great information. We don't have any questions over in the chat console at the moment. As Peter was saying, if questions do arise, feel free to email us at sales@ogipe.com. Also, check out our new website, just recently revamped. You can submit questions there. And I'd also encourage you guys, everyone, to follow OGI on social media. And in the next couple of days, we will be sending out an email to registrants providing an on-demand link of this that will take you to this webinar. So if you missed anything, or if you need a reminder, or you got in late, or anything like that, you can view this very webinar on demand online. So keep an eye on your inbox. In the next couple of days, we'll be sending that out. I'll wrap up with this. Our next webinar will be in 3 weeks. So that'll be August 27th, and that webinar is going to cover Total Arc. So if you are looking into relighters or things along those lines, then please join us for that. And with that, thank you, Peter and Grant, and thank all of you for attending. And we'll go ahead and wrap up. Thanks again, everyone.